In this video we are going to discuss about a common base configuration. So we can study the common base configuration either using a NPN transistor or using a PNP transistor. So here the base terminal is common for, that is, it is commonly grounded, so that is why it is called as common base. The base is common between the emitter and the collector. So here the input current is emitter and the output current is collector. So I can write the current gain alpha is equal to IC by IE. So output current is a collector current and the input current is a emitter current. Usually the alpha value is very less, which is ranges from 0.99. So here the we know that the BJT is a current control device. So let us discuss if I want to act this as amplifier, it should be the input side, that is from emitter to base should be forward bias, and collector to base must be reverse biased. Okay, so here I can write the input. What are the input current? The input current is IE and the input voltage is VEB. That should be a forward bias. So if it is forward bias means I have taken P type at the input, so you have to give positive voltage for VEB. Okay, so VEB must be positive. So the output side you have output voltage as VCB and the output current is IC. So here since P type is there, you have to give a reverse bias for active region. So VCB must be negative. Okay, for to make this common base configuration to work in the active region. So let us discuss the input characteristics. The input characteristics is between IE versus VEB. Okay, so IE versus VEB, you have to change the value of VCB. Okay, VCB. So if VCB value is -1, if VCB value is -1, you will get some value of current for the for this VEB. Okay, for this value of VEB. So suppose if VCB get increased to -5 volt, so that means you are increasing the reverse bias. For the same value you are getting a higher value of IE. Why I am getting means, so if VCB is equal to -5, that is you are increasing the value of VCB, the reverse bias get increased, right? So you are increasing the reverse bias. So if reverse bias is increases, the space charge between the base and the collector get increased. Okay, so this will reduces the width of the base. Okay, this will reduces the width of the base, therefore the IE current get increased. Okay, so this is about the input side. So if you see the output side, we know that IC is equal to alpha IE, and the IC values, if IE values something and this is almost equal to 1, so the IC is same as IE. Okay, so I need to plot the output characteristics between IC and VCB by changing the value of the input current, that is IE. So if IE is 1 milliamps, IC is also 1 milliamps, right? If IE is 2 milliamps, IC is also 2 milliamps. Okay, so this is irrespective of there is a change in the VBC. IE values is similar to that of IC. Okay, so if IE value is less than 0 means it is in the cutoff region, and this is nothing but your active region. since we are increasing the value of VBC, right? VBC. So here I have written VCB. So if VCB is negative, means what is VBC? VBC is positive. Okay. So it is in the active region. Okay. Suppose VBC is negative, means, okay, so it is forward biased. It is forward biased. So the input and output are in forward bias, means that should be in the saturation region. So this cross line is called as a saturation region. Okay. So in that region, the IC value get reduced. Okay, because the same as this one, right? The inverse of this one will happen. So this will reduce the value of IE, therefore the IC value get reduced. So I can write what is the value of IC. So IC is equal to alpha IE plus IC B naught. So this IC is either a DC current or AC current. So this is a DC current and this is a AC current. Okay. So overall I can write alpha is equal to del IC divided by del IE. So here this is having I can use one more topic called early effect. Okay, early effect. What is the early effect? It is also called as base width modulation. Base width modulation. So we know that if the value of VCB is increasing, VCB is increasing means the reverse bias get increased. So therefore the effective base width of the base width get decreased, right? So this dependency of the base width on the collector to emitter voltage, okay, is known as early effect. So if I increase the value of VCB, the base width is modified, right? So this is called as early effect. So if I for the large value of increase in the VCB, the effective base width may reduce to 0. Okay, so this will cause the voltage breakdown in the transistor. So that effect is called as punch through. Okay. So these are the consequence of the base width modulation. There is also another possibility that the minority carriers can be injected into the emitter junction. Okay, this is also possible. Then there is also a less chance of recombination within the base region, because the base region is very much less, right? So therefore these are the three consequences of the change in the effective base width. So from this equation I can derive the value of from this equation I can write IC plus IB plus IC B naught. This also I can write. So I can write 1 minus alpha IC is equal to alpha IB plus IC B naught. So this is nothing but IC divided by alpha divided by 1 minus alpha IB plus 1 minus alpha IC B naught. So this I can write it as beta IB plus This I can write it as 1 plus beta 1 plus beta IC B naught. Okay, so therefore I can write IC is equal to, so from IC beta IB plus IC E naught. This is from common emitter configuration. Okay, so what is IC E naught? From the second and the first equation, so IC E naught I can write it as 1 plus beta into IC B naught. So usually the IC B naught is written as 1 plus beta into this IC B naught, they have written as IC naught in few books. Okay, so I hope this video is useful for you. Thank you very much.